Let's discuss our last piece of statistics in terms of descriptive statistics that we'll use this semester. And this measures of position and a specific type of measure of position that has a special name, z-scores. Um, when we were dealing with reporting the median or the range, which included your observed minimum and maximum values for data sets that are not normally distributed, we can actually add a few other statistics to that list so that we can get a fuller picture of that distribution. And it has to do with specific types of measures of position, like can we get the relative position of observations within a data set? And this has to do with quartiles. Quartiles are values that divide your ordered data set into four equally sized parts. And the way I like to think of this is that we're going to basically, if I can have all of my data represented as a number line, all I'm doing is finding the three numbers that separates the bottom 25% from the next 25%, so on and so forth, right? And these are our quartiles. There are three of them. The first quartile, which you can abbreviate with Q sub 1, that's the median of the bottom half of your ordered data set. Quartile 2 is actually a value that we already have. It is your median, which is the median of all of your ordered data. And then quartile 3, or your third quartile, is the median of the top half of your data set. And so basically, once I find my median of my overall data set, I can kind of separate my data sets into two and then find the median of the bottom and the upper half, and that can give me my quartiles. Now, we're going to do this by hand, and we'll see an example of that a little bit later. But it's going to depend on whether you have an even or an odd number of observations. What I want to make a point with here is that if I have an odd number of observations in my data set, that means that when I find my second quartile or my median, I'm going to have one single number in the middle, all right? And that's going to be my median. When I find my upper and lower quartiles, I'm going to leave that number out and then find the median of each half to get my Q1 and Q3. When I have an even number of observations in my data set, we're going to see how we can calculate Q1 and Q3 in reference to Q1 there. But these are measures of position because they provide information on the relative position of the different values within our data set. We'll be able to know, okay, well, am I in the bottom 25%? I'm in the top 25% just by knowing what Q1 and Q3 are. And that's why these are measures of position. With the quartiles, we can calculate what we call the interquartile range, or what we call IQR. The interquartile range is a range. Remember, our overall range of our data set is the difference between the maximum and minimum values. Well, the interquartile range is just the range from Q1 to Q3. So all I have to do is Q1 minus Q3. It's another measure of variability, and it basically gives us the range of the middle 50% of our data, because Q1 is at the 25th percentile and Q3 is up at that third quarter of our data. And so if I subtract 25 from 75, or 3/4, I get 50%. So that's another measure of variability. If I take those quartiles and add our minimum and maximum values to that, we get what we call the 5-number summary. It's a statistical summary that gives us measures of central tendency, variability, and position, and it's composed of these 5 numbers here. And so let's look at an example where we calculate the 5-number summary, which again is the minimum, Q1, Q2, Q3, and the maximum. It says, suppose an educational researcher wanted to analyze the test scores out of 100 points of a group of students in an intervention group. The scores and the plots are not below. I just have the scores here. And so all I want to do here is give the 5-number summary. Luckily, these values are already in order from smallest to largest. That is always what we need to do because we're going to get the relative positions, right? Now, it's easy once you have these ordered to identify your minimum and your maximum values. That's 2 numbers out of our 5-number summary. And we've already found the median, but we'll do this again. Remember, there are 20 observations. That's an even number. So that means we have 2 numbers in the middle, and they're going to be in the 10th and the 11th position. And so if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, I have these 2 as my middle numbers. Now notice if I add those together and divide by 2, we're going to get the exact same value, right? And so our median, our quartile 2, is that same value, 91. Now, notice I have 2 middle numbers there. Now, when I said earlier in the video, if we have an odd number, when we find the median, we take that out of our data set, and when we want to find Q1 and Q3, we remove that value and just look at the bottom and the upper halves. Well, we don't do that when we have an even number. All we're going to do is separate the data into 2 halves and include those numbers that gave us the median. The 91 is going, this lower 91 is going to go in the bottom half. This other 91 is going to go in the top half. If this were an odd number and my median was just 91, I would remove that and look at the halves separately. All right, so now I have a lower half and now I have an upper half. If I find the median of the lower half, well, there's 10 observations. Oh, that's even again. So if I count to find my 2 middle numbers, they will be 84 and 86. Average those, and my median would be 85. And then if I go to the 5th and 6th positions here, because that's 10 observations, I add those 2, divide by 2, and I get 98 as that value. So Q1 is 85 and Q3 is 98. Now I have all of the values that make up my 5-number summary. All right. Now, there is another graph actually that we can use to graph our 5-number summary. Before I go back there, there is a note here that I kind of skipped over, and I want to review this because this is going to be important. What I just went over is how we would calculate the 5-number summary if we were doing this by hand. There are actually algorithms that different computer software or statistical software use in order to calculate your quartiles and your medians, all right? So if I were to enter this data even in our JASP software, I may get differing values of our median and our quartiles because JASP uses another algorithm. This is the algorithm that we went over on the screen. This is how we're going to do this by hand. If I want you to use JASP, I will be very specific to say, give me the median from our statistical software JASP. Even if I go to R, or if you're used to Excel, or maybe even SAS, they may be using different algorithms to calculate your median and your quartiles. And those algorithms kind of look at the positioning of the numbers and some kind of intricate formulas to come up with these values. We've simplified it by hand, but your computer software uses other methods. So beware of that if you're doing some homework or you're looking at a quiz or some other data and they're getting differing numbers than you are. Usually, if we don't have a large data set, I'll say do this by hand. But if we have a large data set, I'll say put it in JASP, and I'll be very specific as to what method you're going to be using and what number you should give. All right, there's an additional graph that is directly related to the 5-number summary, and these are called box plots. You may have heard them being called box and whisker plots because it looks like a rectangle or a box with some whiskers that are hanging out or extending out from the box. This graph is on numerical data, so it's for interval and ratio levels of measurement. And it's basically giving you your 5-number summary. There's a box, and then we have these whiskers here. And this line segment that is extending from the box on the lower end of this vertical scale, it stops at your minimum value. So in that data set that we just looked at, the minimum was 71. And then the box begins at quartile 1. It ends at quartile 3, and ends somewhere in between quartile 1 and quartile 3 is your median, which is going to be highlighted within that box, which was 91. And then we have the end of the box, quartile 3. And then extending from the box, this upper whisker stops at your maximum value. And so this not only gives us quartile 1 through 3 gives us measures of position, but we also get how spread out our data are by looking at this box plot as well. Like, for instance, there's a huge spread between your minimum value and your quartile 1, but all of your other values kind of have that same spread, right? That means that 75% of our data observations are between our quartile 1 and our max. They have about the same spread, a very similar spread, as compared to our minimum value in quartile 1. That makes up 25%. So our data, while they're very spread, we have less spread between quartile 1 and the max compared to the min in quartile 1. You can see how we can start talking about how spread out our data are. I talked about how our interquartile range, our IQR, was the range between quartile 1 and quartile 3. It's directly related to the spread that makes up the box in our box plot. And that's the middle 50%, once again, because that's 75% minus 25%. Sometimes we like to look at the interquartile range because we may have extreme values in our data set. And that usually happens when our data is skewed. And so a lot of times, instead of looking at the range, which uses the minimum and maximum values, the range is very sensitive to extreme maximum and minimum values. And so if we know that our data set may have extreme values in it, we want to look at the middle 50% of our data to talk about the spread instead of looking at the full maximum minus the minimum. So there's a lot more we can talk about and look at to analyze our data, but this is another plot that we can use in order to describe our data and descriptive statistics. And so now if I want to update this slide on choosing the appropriate descriptive statistics, if I have an interval or ratio variable that's skewed or that's not normally distributed or bell-shaped, then I can just report the 5-number summary and the IQR, and that's enough information for me to know the center of that distribution as well as the spread of that distribution. And so you will probably most often, now that we have this information, see the 5-number summary and the IQR provided for data that are not normally distributed. All right, so your quartiles were an example of some measures of position. You may have heard of deciles. These are measures of position that divide a data into 10 equal parts. And some of the assessments that were given maybe 3 or 4 or 5 decades ago, they will report things in deciles so that you can see or compare children and things of that nature. But another type of measure of position that we're going to be focused on here would be your percentiles. And percentiles basically divide a data set into 100 equal parts. And they represent the value below which a given percentage of observations fall. So if I have a child that's scoring at the 75th percentile, that means that child is scoring better than about 75% of the population of children who's taken that test, or the norm reference group if it's a norm referenced exam. And so I just want to look at an example so that we can interpret percentiles. It says the graph to the right represents the cumulative frequency distribution for SAT scores of college-bound students in a recent year. What test score represents the 62nd percentile? And how would I interpret that score? Well, a graph like this gives the cumulative frequency distribution. We looked at frequency distributions before, and we talked about relative frequencies. Well, in order to do a cumulative frequency distribution, all you do is you add up. I'm going to go to an example from before in our slideshow, and I'm going to make it very, very simple and go to. We have relative frequencies. I'll go to this distribution here. I know this is with categorical data and not quantitative data, but I do want you to see this. So I have a column here that says frequency. I have the relative frequency, and I can add a column that says cumulative relative frequency distribution or a cumulative percentage. All that means is if I start with this category here and I want the cumulative distribution, well, this first category is going to stay the same. But when I go to this license, this next category, if I want to calculate the cumulative distribution, I would take this relative frequency and add to that the previous relative frequency. So 0.9 added to that, I think will be 0.63. And then if I wanted the cumulative distribution or the cumulative relative frequency for this next category, I would take this relative frequency, the 0.03, add to that the 0.54, and add to that the 0.09. So you're basically getting the frequency of that category or that value and all of the previous values that you have already listed in your table. In the example that we have with the SAT scores, they're doing that for all of the SAT scores, which are on our vertical axis. And so when I go and get the percentile, this percentile is going to be representing this score and all of the SAT scores before it. All right, let's look at this specific example related to the 62nd percentile. So again, we have SAT scores along the horizontal axis and the corresponding percentiles on the vertical axis. So if I want to know what score corresponds to the 62nd percentile and how to interpret that, well, I'm going to find the 62nd percentile here. 62 on this scale looks about here. And so I want to back trace that to a point on the curve here. And then I want to back trace that to the value on my horizontal axis, which is about 1600. So the 62nd percentile corresponds to a test score of 1600. So that means if a student gets a score of 1600, they're at the 62nd percentile, which means 62% of the students had an SAT score of that value or less. All right. And so that's something about percentiles. It gives you the score at which you're at or below that percentage. Or that percentage is at or below that score. I'm sorry about that. Our last measure of position has to do with either what we call standard scores or what's more statistical, known as z-scores. This is another measure of position that represents the number of standard deviations a given observation falls from the mean. So percentiles are measures of position based off of dividing a scale into 100 equal parts. Quartiles are measures of position that's based off of dividing a data set into 4 equal parts. And it gives the position of the 25th, 50th, and 75th percentile, basically. But z-scores give the position of observations relative from the mean, and they're in standard deviation units. there's actually a formula for calculating z-scores, which is given here. You take an observation, so a number that's on the scale of your variable, and if you subtract the mean of that scale of that variable and divide it by the standard deviation, you're going to get a z-score, aka a standard score. And basically, remember, it basically transforms a variable into a standard normal variable, and all that means is it's changing or standardizing a variable so that it's in standard deviation units. We're going to talk about the normal distribution, the bell-shaped distributions, a lot more in detail next time. And so that second line here, that this formula transforms any normal variable into a standard normal variable with a mean of 0 and a standard deviation of 1. I'm going to review this next time as we get into our next module. And so if this doesn't make any sense right now, it is perfectly fine. Just know that it's a measure of position that tells us the number of standard deviations an observation is from the mean. We subtract the mean from it, so that gives us a relative position to the mean, and then we standardize it by dividing it by the standard deviation. So this is now in what we call standard deviation units. What I really want you to know right now is that these z-scores allow us to compare variables that may be measured on different scales. I'm using these terms normal distribution and standard normal, normal variable, normal distributed variables a little prematurely here. And so let's look at an example for what I want you to know at this point in relation to z-scores. They usually range in value from -3 to 3. However, a z-score or a standard score can be any value from -infinity to +infinity. But like I was saying, they usually range in value from -3 to 3. We can use these z-scores to determine whether observations are usual or unusual based off of this graphic here. If I find a z-score or a standard score, and it's between -2 and 2, I'm going to say that observation is pretty usual. But if it's more than 2 units from 0, but less than 3 units from 0, so in this range here or in this range here, I'm going to call that standard score unusual. And then if it's less than -3 or larger than a +3, that's going to be a very unusual score. Now, this is going to be based off of that term that I was using, a normal distribution, which we know is bell-shaped, but there's going to be a lot more to come on that in the future. But once we know a z-score, we can say whether that is usual or unusual. Let's look at an example so that we can be more concrete in what we want to know right now. This is a very good example here. It says, assume SAT and ACT, those exams measure similar kinds of ability. The SAT verbal scores have a normal distribution with a mean of 510 and a standard deviation of 100. And the ACT verbal scores have a normal distribution with a mean of 21 and a standard deviation of 4. We have two individuals, Sam and Sarah, and Sam scores 560 on the SAT, while Sarah scores 26 on the ACT, and that definitely should be capitalized. Now, these two are measuring a similar kind of ability. They're both the verbal section, and we know the mean and standard deviation of these normal distributions, these bell-shaped distributions. Who has the higher verbal ability? Well, in order for us to compare two values from normal distributions that are measured on two different scales, what we're going to do is we're going to transform them into z-scores so that they can be in standard deviation units instead of points on the SAT scale versus points on the ACT scale. Different scales, right? So I'm going to go to Sam. This is his information. He scored 56. So in that z-score formula where I saw X, that's going to be replaced with 560. I don't know if I just said 560, but 560. The mean of the SAT scale at that time was 510, and the standard deviation was 100. So for Sam, if I wanted to calculate his Z-score or his standard score, I would take the 560 minus 510 divided by that standard deviation of 100. That's 50 over 100, which is 0.5. Notice here it's a positive and it's 0.5. So Sam score is 0.5 standard deviations from the mean. And since it is positive, it's going to be above the mean. We can also see that Sam scored 560 and the mean SAT score was 510. So it's 0.5 standard deviations above the mean. The positive sign tells me that it's above. If it were negative, I know that it would be below the mean, and that score would be below 510. Let's do the same for Sarah. Sarah scored 26, so Sarah's observation is 26. The mean of the ACT is 21 with a standard deviation of 4. So if I use that same formula for Sarah, I'm going to get 5 over 4, or 1.25. Now, Sarah scored 26, which is above the mean, so I expected this to be positive. If her score was below the mean, this would have been a negative value, because when I subtract a smaller number I do a smaller number minus a larger number, I'm going to get a negative value. All right, so Sarah's score is 1.25 units above the mean, while Sam's score is 0.5 units above the mean. Both are positive, but Sarah is way more above the mean compared to Sam. That means Sarah's score, her verbal ability, is higher than Sam's. Now, we also talked about what values are usual and unusual. Any value between -2 and 2 is going to be considered usual, so they both have scores that are usual. So for now, be able to use the formula for a Z-score. Know that Z-scores are in standard deviation units. If they're positive, that means the score was above the mean. If they're negative, that means the score was below the mean. And values between -2 and 2 are usual. Values more than 2 units from 0 are considered unusual, with being more than 3 units being very, very unusual. All right, that is all for this video here. And that wraps up the content for this week. And so I'll see you in our next lecture video, which will be next week.